Good morning, everyone. You're listening to the Sci-Files, an exposure segment featuring Michigan State University student research. We're your co-hosts, Chelsie
and Daniel Puentes.
This morning, we're joined by Michael Pajkos. Michael, can you please tell us a little bit about yourself?
Sure, Chelsie. I'm a third-year graduate student here at Michigan State, and I'm studying astrophysics.
Thanks for stopping by, Michael. What in particular are you studying about astrophysics?
So I'm looking at the explosive endings of a star's life. And the ones in particular that we're looking at are not ones like our sun, but they're made of much more material. You can kind of think of them as the big brother or someone who watches over our sun because they're made up of so much more mass. Now, the endings of a star, one our sun and one these big ones, is quite different. Our sun will gradually puff up and it will cool down. But these ones are much more explosive. They're a lot more violent in a way because they're very unstable when they run out of fuel. And so when you think of stars, you can just think of them like engines in a car. In order to run the car, we put some fuel in and we can go so far down the road. With stars, it's kind of the same way. They have so much fuel that they can use, and at the end of it, they go kaput. In this case, these things just explode.
You mentioned that you particularly focus the death of a star, but I'm wondering, how does the life of a star look?
That's an interesting thing to think about because a lot of what I work on a day-to-day basis are just those last few moments, how a star experiences its life, if you will. And throughout the course of it, though, it has a very interesting beginning. So we begin with some kind of cloud, if you will, a cloud of gas, and it's mostly made of hydrogen, like you would find in a blimp or a balloon, maybe. And over time, this hydrogen will slowly pull in on itself, kind of snowball. That's what the force of gravity will do. It pulls it together. As it gets pulled together, you can imagine with a pressure cooker. As time goes on, it will get crunched more, and that temperature goes higher and higher and higher. Eventually, that temperature will cause it to ignite in a sense where you have this nuclear burning where a lot of heat is being released at one time. That is typically in astronomy where we define a star beginning its life. So the sun, we have a pretty good idea. It began its burning around 4.5 billion years ago, and it maintains roughly its spherical shape. Now, it's interesting, though, to astronomers and other people who are astronomy enthusiasts, is that as time goes on, the sun slowly expands. It's actually growing. And so what you can think about is kind of an analogy with a campfire, where on a cold winter night, you want to stay close to the fire. If you were to throw more wood on the fire, or that fire were to get bigger, it would get warmer and warmer as you got closer and closer to it. And so that kind of has implications as well for as that sun continues to grow, it's going to slowly move out that certain zone, if you will, a Goldilocks zone where it's ideal for life to form.
Since the nearest stars are so far away from Earth, how are you even studying what happens when these stars die?
That brings up an important point in astronomy because with all the other sciences, or most of them at least, we think of chemistry, we can go into a laboratory. We can conduct an experiment with certain chemicals, and we can repeat that experiment over and over and over again. Astronomy is a little bit different because we can't just create a star out of nowhere or create a planet so we can examine life. What we have to do is use the cosmos as our laboratory. And what that means is we have to look at other things. So the sun is the clearest example of a star that we look at, but we have to look even further and deeper, trillions of miles away from our home planet, the Earth. So what we do is we leverage the power of telescopes, the idea where we mix lenses and mirrors together so that we can capture light. Similar to catching water in a bucket, we just catch light in these telescopes so that we're able to start to get images of these other stars. And by looking at more and more stars, we can get a better example of the stellar population or group of different stars out there so we can start to draw bigger conclusions. So instead of conducting the experiments ourselves, we're just observing what we have at our fingertips.
What can people observe from images from telescopes? Do you particularly capture images with telescopes on campus?
MSU has a really interesting astronomy department because of how broad each of the subjects that they can investigate is. They have an observing program where they have access to these telescopes that are thousands of miles away on other continents. For example, in South America, in the Andes Mountains, we have a telescope called SOAR that we're exposed to. And a few years back, I was actually fortunate enough to visit it. So I had to take a 9-hour flight south, We got to the Chilean capital, which is called Santiago. We took a 7-hour tram ride north into the mountains and 9,000 feet up in elevation, and we got to this beautiful landscape. It was incredibly dry. You couldn't see anything except for a little goat farm down in the valley. And that's really the key when you want to find locations for these new telescopes, because you want to be away from all the light you can. The only light that you want to get is coming from the stars themselves. But you asked what I do in particular. And while Michigan State has a variety of observational programs where you literally take and examine the images yourself, I like to work with more or less what-if scenarios on the computer. We could call these simulations, if you will. And like Danny brought up a little bit earlier, we can't always make stars and we can't make planets at our own whim. We have to just look at things. Likewise, we can use computer programs to play through these what-if scenarios and say, okay, if I had a star that was this big and we hit the fast forward button on our computer, let's play through a star's life in a matter of minutes for us. But for it, it's experiencing billions of years. And what this allows us to do is draw conclusions and say, okay, even though I can't see every star in every scenario, what I can do is prepare myself. And if I investigate enough of these what-if scenarios, then I can start to get a handle on what kind of signals we can expect, whether a star is humming along throughout the course of its life, or whether it's going through a rather violent ending, like an explosion.
So then to call back on that example you used earlier about making a star in a laboratory, how do you make a star in a computer then?
Yeah. You don't want to light the computer on fire or anything like that.
Right.
So this is where the math comes in. And I think a lot of times math gets a bad rap that, oh, it's that subject in 4th grade that, I had to memorize my multiplication tables, or it's super dry, solving for X and all that stuff. But the more that you get into it, the beauty of math lies in the fact that you can describe the world around us. So for example, an instance in which math is used every day is at certain turnpikes and certain highways. You can't have a cop at every single mile to check if people are driving safely. And so what they use are these toll booths, and you clock in and you mark the time that you started, you travel a certain distance, and you clock out. And they can calculate your speed and say, okay, if you went this distance and under this amount of time, then you were speeding. You don't need to waste resources. You don't need to waste people's time. Cops are doing something else to keep people safe. Math has a lot of different ways that you can leverage so that you can examine the physical world. And some of those are describing the different parts of a star. So gravity is the force that pulls us down here on Earth. If you trip down the stairs, if you drop something on the ground, it's going to pull it downwards or inwards towards the center. And we can describe that mathematically. And so we have one piece of the puzzle where we have some equation for math that describes everything as being pulled inward. But when we look up in the sky, the sun looks like a sphere or a ball. And so we need a piece of mathematics to expose or describe the fact that something is pushing outwards. So some people may have heard of Einstein's famous equation, E equals mc squared, the idea that the material that we interact with, something called mass, is the same as energy or heat or something that causes things to move. And so by using math to build different pieces of a star and accounting for those different factors, we're able to describe a physical scenario.
When you're running these simulations for the death of a star, what actually defines an explosion or another scenario?
So we have different students in our research group who are investigating the different kinds or the different avenues that a star can take at the end of its life. So the 3 of them that I could think of off the top of my head are, one that's rather boring, it's kind of a fake explosion, or a dud, if you will, where it really doesn't have enough energy to go kaput and blow all of its material out into interstellar space. Just kind of, it's a failed explosion, if you will. The second one, which is a little bit more interesting, is it implodes on itself. And you can think of that kind of like a vacuum cleaner, everything getting sucked in and being compressed down into a very tightly bound ball, something called a black hole, if you will. And the last ones that I'm particularly interested in, is what happens when there is enough energy packed into that star right before it goes boom, that all of those materials just get flung out into interstellar space. And we basically kind of put signposts on the outer parts of the star, if you will, and we track okay, once it goes this far and it's moving this quick, we can safely assume that it's not going to fall back in on itself. And with that, we can deem it a successful explosion.
And what happens to the star after the explosion? Like, what happens to the material afterwards?
That's a good question. Ever since humans have been walking on the earth, we've gazed up at the night sky and we always wonder, how did that get there? How did we get there? It kind of instills that sense of wonder in us when we're little kids. And I've always chased that, which is why I'm still in this field for a career. And where those materials go, they go to a variety of places. Some of them fly into other stars, and they give them different elements that they can burn, and we can start to observe those with their light. Some of them go to other clouds that will form stars in the future. Some of them will just stay as these clouds or these nebula. And the ones that are probably the most interesting to all of us listening today are the ones that land on other planets, like the Earth. All of the oxygen content in the human body, the gases that we breathe, the water that we drink, these all come from these stellar explosions. And the one big thing that ties all of humanity together is the fact that the material in our bodies was forged in a star that blew up. And so when you ask, where do all these elements go? Some of them go into the stars that we're seeing, and some of them come from the stars that make us up today. So in a funny way, we're kind of stars staring at stars.
You mentioned earlier that one of the ways that you're able to observe stars in space is through collecting the light through these different telescopes. Are there any other different methods that exist right now that astronomers can use to also know whenever these stellar explosions are happening?
There's a variety of methods that can go into whether we detect something or a star exploding or things colliding together in outer space. And the ones that I'm most particularly interested in are something called gravitational waves. And what these are, you can think of them like ripples on the top of a pond. So as an example, if I were to throw a little pebble into a pond, it would give these very shallow waves that move out towards the outer parts of that body of water. If I were to jump in and do a cannonball, I would get much larger waves that would ripple onto the beach as well. And so in a certain sense, just by looking at the waves, you can tell what created them. If it's a very shallow wave, it would be something very small. And if it was a very large wave, you could probably safely assume it was something very big. Instead of water, however, we're looking at the reality that we live in, something called the fabric of space and time. And you can literally imagine it like a piece of fabric. And what causes these waves can be a variety of sources. But in the context of these exploding stars, you can think of them, well, we're in a radio station right now, you can think of them like going to listen to live music or going to a concert. If you were to plug your ears and you were to watch the concert the whole way through, you'd get a pretty cool light show, you'd see a lot of smoke, and hopefully you'd see one or two cool guitar solos. If you flip the script, however, and you opened your ears and you closed your eyes, you'd get a completely different experience. But you'd still be getting information about the concert. That thudding you feel in your chest when the bass goes real loud, or when there's a high shrill on the guitar that you can feel in your ears. This is the analogy between looking at things with your eyes and feeling them with your body. And so the same game is played with these explosions. We're not looking anymore with our eyes or our telescopes, but we can set up sensitive instruments to feel the ripples and the waves that they're giving off. And this is really unique because this allows us to see and peer into these stars, into locations where light has never been able to show us before. This is information that isn't coming from the outer shell of something where light is trapped, but it can tell us about what's going on. What's the engine that really makes these stars go boom at the end of their lives?
2 years ago, a group of scientists announced that they had, for the first time ever, successfully measured the interaction of gravitational waves with matter here on Earth. In regards to these stellar explosions that you're interested in studying, have there been any gravitational waves that have been measured from these explosions in the first place?
We haven't detected them yet, and I use yet very carefully. So these explosions, the ones that we've seen with light, at least, with these other telescopes, these are ones where we have a pretty good estimate about how often they happen, around, let's say, once every 50 to 75 years, which isn't too good for me, but we are actually overdue for one to happen within the Milky Way. And the reason why I say within the Milky Way is because the instruments that we use to measure these things, they're extremely sensitive. They can measure very small changes in their properties, which is how we get that signal. Now, the reason that we want this information and we need these what-if scenarios is that if these instruments that can detect these gravitational waves have a shape or a template that they can expect, then they have a much easier time viewing this event occurring. So an example I like to think of is Where's Waldo? When we look at a book and we look for Waldo, we know we're looking for that famous white cap with the red ball on top, and he's got the glasses and the white and the red stripes. Because we know we're looking for Waldo, we can find him. If I just said, "Where's Waldo?" and I didn't tell you what Waldo looked like, you'd probably have a headache and you probably wouldn't be able to find him either. Same cases for these things. We're showing the observers, we're saying, this is the shape that you should expect. This is the kind of signal that you can receive. And because they have something that they can expect and they know where to look for, then they're going to have a much easier time finding Waldo or those gravitational waves.
You just mentioned that the Milky Way itself is actually due for a stellar explosion soon. What does that mean for us?
We can get a lot of exciting information from something that were to go off in the Milky Way. Thus far, we've seen these explosions very far away or in galaxies orbiting the Milky Way, but one that would be so close to home would be such a rich place for information because that signal is going to be that much stronger. We're allowed to get information that's much more accurate. If you think about looking at someone very far off in a field, you can't tell the features of them very well. You just say, oh, that's a person that's pretty far away. And the closer that they get to you, you can start to make out, oh, that's the color of their hair, or oh, they might be this tall. The same thing goes for these explosions. The closer they are, the better the signal, and the more accurately we can determine their characteristics. And so not only would we be able to get a handle on these gravitational waves or these heartbeats that are coming from the stars, but we would also be able to tell things like what kind of material are they made up of? How much of this oxygen can we get that's implanted in our bodies? And ultimately try to answer that philosophical question on how human beings are connected to things up in the cosmos.
Thanks for that comprehensive view of your research, Mike. We really do appreciate you for sharing that with us. But what got you motivated into pursuing a career and degree in astronomy in the first place?
So at my undergraduate institution, Butler University, I actually used to be a mechanical engineer. And that was kind of the classic career path that I wanted to follow ever since I was little. But a couple years into my studies, the astronomy track was offered. And I said, oh, I've always liked those, the big pictures in the space books or those interesting programs on the Discovery Channel or whatnot, because I'd always had a curiosity for it. And I said, okay, I'll give it a try. And the more I took these astronomy and physics classes, the more I fell in love with it, because it really gave me an idea about how the universe worked. And the fun thing about studying space is it really grants you some nice perspective, that when you really zoom in way far out beyond the Earth and you look at it as a really tiny blue dot, we're really all in it together, where we're all on this rock flying around our sun, orbiting around a huge black hole in the middle of the Milky Way, and it just gives you a nice perspective that you can take with you in life. And so for those students who are interested in pursuing their studies, and maybe they're going to college or maybe they're still in grade school right now, I would say keep chasing what you're interested in, because the journey is a lot more fun than just doing something that you're expected to do.
What are ways that the local community can get involved with amateur astronomy around here in the mid-Michigan area?
We have a lot of great resources here on Michigan State's campus. If you want to learn a little bit more about astronomy and kind of the overall context about where we fit into things, I'd recommend the Abrams Planetarium. Throughout most times of the year, they have a lot of great shows that can talk about things from why we have seasons on the Earth to, I was at one last year, and it was just a laser light show for Pink Floyd. So not as much astronomy, but because the album was called The Dark Side of the Moon, they invited the public over. And so they have a lot of great outlets for you to learn a little bit about outer space. And if you're more interested in getting your hands dirty and actually maybe looking through a telescope, the MSU Observatory, they have nights that are open to the public. And this is a telescope. It's 24 inches in diameter, And it's a really interesting instrument. I was actually just volunteering the other night for International Observe the Moon Night. And although it was rainy, there's a variety of different outlets and activities that the observatory has that the public can use. And, hey, I want to learn a little bit more about space. Let me talk with some either graduate students or experts like professors who are actually spending their time there instead of sitting at home. They're interested in getting out in the community and sharing their expertise with the public as well.
Thanks, Mike. Hopefully some of our listeners take advantage of some of those opportunities that you gave to us. Thank you for joining us this morning for this interview. We really do appreciate it.
Always a pleasure. Thanks for having me.
Finally, thanks to our programming director, station manager, and general manager. Thank you to all of our listeners that joined us this week. And remember, the truth is in the science. Any comments and questions can be directed to Sci-Files at impact89fm.org. We'll see you all next week on Sci-Files.